So I have a review question here to think about Lenz's law in a few different scenarios. I have a conducting loop and a bar magnet, and the bar magnet could be moving towards the loop with the north pole closer to the loop, or the bar magnet is moving away from the loop with the south pole closer. And then in the last scenario, we have a bar magnet at rest relative to a loop. We're going to use Lenz's law to tell us what the direction of the induced current and induced EMF is in each of these loops. There's a little perspective implied here, so trying to see the magnet in the plane and the loop is perpendicular to that plane, but just showing it a little tilted. So the first thing I want to do is trace a magnetic field line associated with this magnet. So this is the North Pole, so there's going to be a magnetic field line going from left to right, and we'll call that the applied magnetic field. If this bar magnet is moving closer, then this magnetic field that's threading through the loop is getting stronger, and to oppose that change in the magnetic flux through the loop, I'm going to have an induced magnetic field that points to the left. To get a magnetic field pointing to the left at the center of the loop, I'm going to have an induced current and an induced EMF that are circulating around counterclockwise. So that's the direction of the induced current and the induced EMF. And that's for an observer over here on the left. Okay, now let's see what scenario holds if I flip around the polarity of the magnet and reverse the direction of the velocity. So now I can trace a magnetic field line that's going to be threading through the loop, and it is going to be pointed in towards the south pole of the magnet. The magnet is moving away from the loop, so the strength of the magnetic field threading through the loop is going to get weaker. To oppose that change in flux through this loop, I'm going to have an induced magnetic field that points to the left again. And that induced magnetic field, by our third right-hand rule, is going to be caused by an induced current and EMF that circulate around the loop counterclockwise. And again, that's for an observer viewing that conducting loop from the left. Now, for your own practice, you should consider the case where I don't reverse both of those things, but I reverse just one at a time. So try on your own a case where I keep the same polarity but have the magnet pull away, or I reverse the polarity but still have the magnet move towards. And in both those cases, you should find that the induced magnetic field flips around, and therefore the direction of the induced current and the EMF also flips around. I wind up with the same induced magnetic field here because I changed two things: the polarity of the magnet and the direction of motion of the magnet. All right. The last one we want to consider, and just make sure everyone's on the same page with this, there is a flux threading through this loop, because I'll have, for example, magnetic field line pointing from left to right. So the magnetic flux threading through my loop is not 0, but it's constant. Since the magnetic flux is constant, its time rate of change is 0. Time rate of change of the magnetic flux being 0 means there is no induced current, no induced magnetic field, no induced EMF. So B induced equals 0, I induced equals 0, and the induced EMF from Faraday's law of induction is also 0. For there to be an induced EMF in this conducting loop, some aspect of the magnetic flux has got to change. Either the strength of the magnetic field, or the area of the loop, or the orientation of the magnetic field relative to the loop has to change in time. If the flux remains constant, then the induced EMF is always 0.